Hi, this is Liu Fan. I am an assistant professor in computer science at UNC Charlotte. Today I'm going to talk about an empirical evaluation of location privacy. The work is done with my student Yisheng Gold. It is presented at SIGSpatial 2021. Location data is critical to many applications that provide services or enable research. For instance, app users may receive recommendations based on their current location. Furthermore, research studies, such as those on mental health, may utilize GPS traces collected from individual participants. While location data is extremely useful, it is also personal and sensitive. Furthermore, location data may be leaked. Moreover, protecting consumers' privacy is one important mission of the FTC. As a result, applications must pay close attention to the protection of location privacy. The research community has developed many location privacy methods over the last decades. A recent survey reviewed more than 60 location privacy methods. To ensure the depth of our study, we focused on those methods that adopt a local privacy model and sanitize data in an online fashion. The local model ensures that users rely on their own device to ensure privacy and send only sanitized locations out of the device. Users will have a greater sense of control as they do not rely on any other parties to protect their privacy. Location privacy methods that are online generate a sanitized location given the current location and/or historic data, without knowing future places the user would visit. The advantage of those online methods is that the sanitized data is shared with the server immediately, which is helpful for real-time applications, such as traffic monitoring. Location privacy methods that are local and online hold great promises for practical deployment. First, the setting is analogous to the local DP model for non-location data, adopted at Google and Apple as an example. In Android, users can choose to share less precise locations with apps, which can be seen as a simplified approach to local online location privacy. Thirdly, there have been research efforts to open source local online privacy methods to help developers integrate location privacy in their applications, such as the GeoPlay4j repository. Despite the promise and open source efforts, there are significant challenges in the adoption of location privacy in applications. The first is to understand the impact of location privacy on usefulness. Prior studies adopt simple utility measures, for example, measuring the distance between the input and the sanitized locations. Therefore, it is not clear how location privacy may affect the usefulness of specific applications, such as predicting a user's mental health state using mobility patterns. The second challenge is to understand the empirical privacy protection. The privacy models of existing methods are not comparable directly. For example, data deletion versus adding dummies versus differential privacy-based. It is not clear how existing methods may mitigate practical attacks, such as membership or attribute inference. The third challenge is to understand the computational overheads of location privacy. As the privacy methods run on client devices, overheads are very important factors for deployment, but understudied so far. The goals of our work is to address the challenges with an empirical evaluation of location privacy methods. This study includes the following location privacy methods that fit local and online criteria. They fall under three categories. First, there are generalization-based methods, which report less accurate data. One example method is rounding. Essentially, a grid structure with s-kilometer spacing is established in the geospace. Every input data will be rounded to the nearest grid point. The second category is perturbation-based methods, which introduces random noise in the data. As an example, the geo-indistinguishability notion is based on differential privacy, and it can be achieved with the Laplace method, which is shown in the figure. Given an input location, the reported location can be drawn from the planar Laplace distribution. The third category is dummy-based, where real location data is hidden among dummies. For example, in the spot-me method, a user can claim to be at multiple locations in the grid, where only one cell reflects the true location. Our empirical evaluation adopts two GPS traces datasets representing different transportation modes in order to evaluate location privacy in practical scenarios. The GeoLife dataset includes data from 182 participants, and the Real Buses dataset includes more than 14,000 buses. We perform spatial and temporal discretization in each dataset. The two-dimensional geospace is partitioned into 300 meter by 300 meter grid cells. For each user, we subsample the GPS records every 5 minutes and generate one trajectory for each date. The number of trajectories per user and the number of unique locations each user visits greatly vary. We summarize dataset characteristics in Table 1. To evaluate the usefulness of location privacy, we adopt generic utility measures as well as task-based utility measures. First, we include the Hamming distance and Haversine distance between the input and the sanitized locations, and report the average distance among all users' data. We also include 7 mobility metrics, which were designed to predict mental health. Those metrics were extracted from the original and sanitized trajectories, and the relative errors in percentage are reported. An average error among all mobility metrics is computed to show the aggregated trend. Moreover, we evaluate the usefulness of the sanitized data for aggregate queries, such as visit frequency for each location and answering two-dimensional range queries. The mean absolute error to the ground truth, which is computed using the original location data, is reported. For each experiment, we vary the privacy parameter of every location privacy method to observe its impact on utility. As expected, a stronger privacy often leads to lower utility. We measure the empirical privacy risks in sharing location data by conducting privacy attacks. Successful attacks indicate high privacy risks and vice versa. One type of risk is re-identification, where an attacker has some prior knowledge about a target and tries to re-identify the target records in the sanitized data. Using the original clean data, most of the users can be re-identified with no more than 4 locations. Some users are not unique, therefore labeled as non-re-identifiable. In general, after applying a location privacy method, fewer users can be re-identified and more users are non-re-identifiable. Another type of risk is attribute inference, where the attacker has some prior knowledge about the target and tries to infer more. Here, we assume a strong attacker who knows all but 1 locations of the target. Looking at the attack results using the original data, more than 90% of the users are susceptible to inference attacks without the protection of location privacy. After applying location privacy methods, the risks are reduced to various extents, depending on the method and parameter value chosen. To measure the computational overheads of location privacy methods, we measure the CPU time for sanitizing 1 location and the peak memory consumption by each method. We show that all local online methods are very efficient, and we're working to improve our methodology for extending the evaluation. Given limited time, we will not be able to present and discuss thoroughly all evaluation results. Application developers and researchers will find a complete set of results and discussions in the paper, which will help them comparatively evaluate those location privacy methods. The implementation of the studied methods is available in Java, and we plan to release the experiments conducted in this study as a standard testbed. Our results showed the classic methods could defend against privacy attacks as well as the differential privacy-based method. We also showcased the vulnerabilities of deterministic privacy methods with improved privacy attacks, where an attacker may apply a deterministic method to match the sanitized data. Lastly, we will study user preferences for location privacy and validate our results with human subjects in order to facilitate the adoption of location privacy. This research has been supported in part by the National Science Foundation. Please feel free to reach out if you have any questions or comments. Thank you.